first of all, let's introduce ourselves. I'm Danish. I'm going to be senior here. I'm a tennis player, which is one of the main inspirations for our projects. I also have degrees in physics. I've taken both AP Physics 1 and AP Physics C. And in the future, I'm going to study computer science at CU.
Hi, my name is Adhi Basker, and I'm a senior at Grandview, and I've also been playing tennis for the past 4 years. And through an internship opportunity last summer, I gained a lot of experience in web development languages such as JavaScript, Cold Fusion, Node.js, and also database languages such as SQL. And I've also had experience coding in Java through AP Computer Science and other elective classes offered here at Grandview, and I also plan on majoring in computer science.
Alright, so first let's talk about our project descriptions. First of all, we wanted to make an application primarily for the Android that we could place at the edge of the net so we could predict where the ball would be. Because both of us play tennis, especially at the high school level, there's no referee to draw balls. So it's the person that receives the balls, they get to decide whether the ball is in or out. Now, obviously, as you can imagine, at the high school level, that results in a lot of cheating and even just miscalculations on the opponent's part, even if it's not intentional. So what we wanted to do was make an application that uses physics and the camera software to accurately predict where the ball will land. One of our main inspirations was, if you've ever seen professional tennis, whenever a player doesn't like what the official ref calls, they get to challenge. And what the challenge is, it's a Hawkeye program that basically creates this image and basically determines whether the ball was in or out using their own physics software. Now let's move on to the logo design. That's our logo right there. As you can see, it's a deconstructed tennis ball based on the flat, squarish with curved edges. We wanted the shape to represent an app design on an iPhone or an Android. You see the white lines to represent the curves on a tennis ball. We chose the colors green. The color green because it represents balance and harmony, so we have the integrity part of it. And the blue represents the cutting edge technology and trust, so we wanted to include that on our consumers. Additionally, you can see that the shape that it makes is an eye to, it's the ball and where it's going. And finally, we have line genie around the edges, and that's kind of in like a childish font, like how a third grader would write it, and we want that to emphasize ease of use for our application.
Okay, so my project objectives are as follows. So the first is to learn how to use Android Studio and to build a working application in Java. So Android Studio is something that I haven't really had much experience with in the past, so that was definitely a big part of my objectives. And also, my second objective was to achieve proficiency in the usage of OpenCV, which is a computer vision library. And that's the most important part of my project because that's what I need to use to analyze the ball pathway in real time. The next thing is understanding the physics principles behind what happens to the ball when it's in the air, or like the forces acting on it. Although that's not an explicit part of my project, as I'm not the one actually coding the physics engine, it's still important to understand and recognize these principles so that I know what data values to pass to my partner. The next thing is research the process of app publication and hopefully market line genie with the ultimate intent of putting it on the Android Play Store. This isn't something that we were able to accomplish, but it was an initial objective. And lastly, it's just to gain an understanding of computer science as a pathway and just complete a job shadow and work collaboratively with my partner to achieve our goal. So the technology that I used, it's first Android Studio. That's an integrated development environment, and it's what most people use to develop Android applications. There are also emulators that are built into the Android Studio software, which can be used to test out your applications. I initially started using Android Studio emulators to test my application, but what I realized was that this would be really cumbersome and awkward because I had to go to the tennis courts in order to test my application. So if I were to use an emulator, I'd have to bring my computer every time. So that turned out to be, that wasn't a great idea. So instead, I switched over to a Samsung Galaxy S7. So for application testing purposes, and that proved to be a lot better. And it also simulated what the actual application would be like if someone were to use it on their phone. This entire application is programmed in Java, and it's what I'm most comfortable with. And lastly, a big part of this is also OpenCV, or a computer vision library used to analyze ball pathways in real time. So, accomplished research. So here's just a broad understanding of what I did, and I'll go more in depth as we go on. So first of all, I gained a solid understanding of Android Studio, which is something I didn't really have any experience in before. I also gained proficiency with the OpenCV software, and this includes basic classes like the Math class, and also more complex ideas like image processing and layer masks. And lastly, I also understood the physics principles behind what happens exactly when the ball is hit and it acts as a projectile. So that was a pretty big part of my project as well. So this is kind of the first part of my project. I was tasked with initially creating the application user interface. So initially I had a lot of ideas for what I should do for this, such as creating options that would allow the user to analyze or quit or start the program or run the timer or whatever. But all of these things in the end were not really necessary. So ultimately this is what I decided on. What you see on the left is the graphical user interface. So I decided to keep it simple, and which is kind of what you need for an application. So that I have a minimalist design right here, so that ensures ease of use for anyone who wants to use the program. And the two pictures on the right kind of represent, one, the XML files that you need for Android. So XML is actually a pretty crucial component because you can manipulate what the users see in the user interface by changing certain things. For example, right here we see Android layout width, layout height, and all of this pertains to this record button right here. So instead of actually going in and changing the scale of the record button itself, you can go into an XML file and instead change those things. So that was something I learned about as well. Another thing is just basic Android file structure. So the first part of my project was creating an on-touch color function. So this wasn't actually integral for my project to work, but I still needed it because it made everything so much easier. So this is pretty self-explanatory. What this does is when on the event that a user touches a certain part of the screen, it returns the color value of that part. And then I end up converting this color value, which is in hexadecimal, to hue saturation values. So the involved concepts in this were first, the math class and associated classes. The math class is basically the one class that's pretty much the most important thing that you end up using in OpenCV. It's basically a matrix, and classes like submat and rect are just, I guess, just subclasses of that predefined matrix. And also I learned about color conversions. So for example, RGB to HSV, that was something that I had to use to convert my RGB values to hue saturation values. And there were others such as RGB to grayscale and things along those lines. Also, core.sum elements. That was a pretty big, that was probably the most important operation in creating the on-touch color function. What this does is it takes the average value of all the colors in a certain submatch or a certain submatrix, and it adds those up and it returns the average color value in hexadecimal. And you might be wondering at this point, why is a touch event necessary to analyze the pathway that the ball takes? Well, the thing is, everything that the application really recognizes is from hue saturation values. So the way that the application really finds the tennis ball as it's passing over the field of vision of the camera is through analyzing hue saturation values. And therefore, that's where this function comes in, core.inRange. So this takes two main parameters, a lower scale or a lower bound of hue saturation values and an upper bound of hue saturation values. So if the application detects anything that's in front of the camera that is between those two values, then it returns that. It creates a mask essentially, and it returns that as white. And everything that's not in that range gets returned as black. So also, you might not understand this now, but I have graphical representations of this later. So creating this on-touch color function was important because that's the only way that I could manually determine what the hue saturation values of the tennis ball were, and then use that subsequently to create the ranges, which would then be used to find out, which would then be used to locate the tennis ball actually. So here's just some examples of what the onTouch function did. So as you can see here, with the tennis ball, it returns the hexadecimal color value based on the sum elements function. And same thing with my Spanish finder. So it returned whatever this color here was. So now we move on to the bulk of my project conceptually, which is morphological image processing. So the main problem here is that even though I managed to create a layer mask with the ball getting returned as white and the rest of the output getting returned as black, the main problem is that there could still be instances where certain parts of the ball are not caught or not recognized by the Android camera. For example, if there was bad lighting or if a part of the ball was discolored, then what would happen is that that part would not fall under those HSV values, which would then be recognized as black. So what this could cause is unnecessary holes in your ball or just not a clear image. So that's where morphological processing comes in. So there are two main operations that are used in morphological image processing. The first is image dilation. Essentially what that does is it enlarges pixels that are black that are close to other pixels that are white. So, it enlarges the white pixels to make sure that the holes in an image are essentially filled up. Erosion is kind of the opposite thing. It takes away background noise from your image, so just in case the camera was picking up something that wasn't supposed to be part of the tennis ball, it gets rid of all of the background noise to make a cleaner image. So that's what I was talking about here. So as I already said, if there's excessive background noise, then you use image erosion, and if there's ball grooves or markings that are not part of the typical hue saturation values of the tennis ball, then you use dilation, which basically fills up those holes in the image that were black with more white pixels to create a full image. So I used two calls of both. So I used dilation twice and erosion twice to maximize to maximize the image output. So here's what I was talking about, the code here. So I used this core.inRange function was what I was talking about. It inputs an HSV image and also the min and max values, which are both scalar quantities. So then from there, what happens is it outputs this masked image, which basically has the tennis ball getting returned as white, or whatever it detects getting returned as white, and the rest of it getting returned as black space. And then from here, I use dilation and erosion twice, using the core.inRange output as my input for these two functions. And then whatever gets changed is returned as your morph output. So just for, to increase understanding of this is what happens as a result of morphological image processing. So as you can see, there are a lot of, these are actually pictures that I took from the application. So as you can see, there's a lot of background noise here. So we obviously want to get rid of that. And this is where the tennis ball's grooves are. So those aren't going to be the same color, obviously, as the rest of the tennis ball. So that's why there's a little hole here. But through image processing, we can fill in those holes and also get rid of this background noise. Also, the next part of my project, after getting through the image processing side of this, was finding and drawing contours. So essentially, what this is needed because you need to pass coordinates through the form of a rectangle. So essentially what happens is you need to draw a rectangle around the detected tennis ball so that you can later pass coordinates in terms of the width and height and the position of the rectangle itself instead of the tennis ball. But again, the problem with this was that there were too many rectangles to start off. When I initially implemented this function, the code said to draw rectangles around every part of the application that showed up with white space because that was what was recognized by the program. However, even with the image processing, there was still a lot of white space and background noise left. So that's why we see images like this. So it's drawing a main rectangle around the actual tennis ball, but also these smaller rectangles that were because of the background noise. So as you can see, it got slightly better, and eventually I got this output, which is ideally what we would want, so that the tennis ball, so that there's only one rectangle drawn in the entire grid, and that's for just the tennis ball and not the rest of the background noise. So there are a couple of obstacles that I had to endure in this program, in this process. First is a lack of familiarity with OpenCV and Android Studio. I mean, those were pretty easily overcome just through research. Also, there were initial problems with downloading and importing OpenCV software as a module. I think I forgot what exactly happened, but I kind of had to restart the entire process, start a new application, all that, and that seemed to work there. Also, I didn't have an Android phone to test my application, so that would be a significant problem because this is an Android app, and I don't have an Android phone to test. So I got around this by just using one of my old phones and also not using the emulator from the camera anymore and actually using my sensor. So that solves that as well. So there's also issues with precision of the tennis ball. So a question that you guys might have is, with the tennis ball traveling so fast, especially in like pro serves, when they serve at like 100 miles per hour, like how do you expect to gather coordinates of the tennis ball without the program glitching or just not detecting the ball whatsoever? And turns out all we needed was an approximate image of the ball instead of the whole thing, because with image processing we could later fill in the holes and get rid of the background noise to isolate the ball itself. So that also wasn't an issue, but initially I was confused because I didn't use morphological image processing, and that resulted in very poor output for the tennis ball detection. And lastly, there are just difficulties keeping up with my timeline. I was kind of behind on my timeline throughout this entire process. I only really caught up with my timeline around April, but that was an issue as well, but I was able to overcome it. So outcomes and accomplishments. First, I created a clean application user interface, as I already showed you guys. Completed extensive research in image processing. Successfully completed object detection using image processing, the two operations, dilation and erosion. I passed a series of coordinates and times and areas to the physics engine, so that the physics engine now has the x, y, and z coordinates as its input, as well as the different times at which those measurements were taken to calculate velocity. Lastly, I ran statistical analysis during the month of March with my partner to determine program accuracy and just see where we were at and where we could improve. And
So these are my project objectives. The first one is learn how to use IntelliJ advanced math libraries. IntelliJ, like Android Studio, is an integrated development environment. It's basically where you write your code, where you compile your code, and where you build your code. So because of this, I need to learn how IntelliJ works. Previously, I have used IntelliJ in the past, especially in computer science and some other coding programs that I went to. So I knew how to do that, but I wasn't really familiar with the class structure and the file structure that IntelliJ uses to help make my life easier, which ended up turning out to make my life harder, which I'll get into later. Secondly, I have to learn how to create efficient code to problem output. When we get to our timeline later, my part of the project was to basically make a physics engine to predict where the ball will be going after it gets the coordinates. But in my timeline, you'll see that actually making the physics engine doesn't take that long. It's actually optimizing the physics engine so it has a very small calculation time that can determine whether the ball was in or out before, the players continue playing. So it's very important to have a very fast reaction time for the program. And that's something I need to learn how to do. And something that didn't quite happen, or number 3, is researching the process of app publication. Due to the many failures that happened in the second semester of our project, we weren't able to actually get our app ready for publication, so that's why that didn't happen. Me and my partner also committed various statistical trials to see the actual accuracy, and we'll get to those later. And finally, it's basic physics, learning the effects of drag on the ball. If any of you taking physics 1 or C, you guys learn drag in 1 dimension, but it gets exponentially harder in 2, and even more so in 3, and I had to learn about that. And to make a drag function for my my research and accomplishments. First, I fully researched the effects of drag on the ball. I found a website, did a study with the University of Washington that helped me a lot. It found everything that I needed to do the calculations, and I'll get to that later. Compilation and execution. So this is basically a chart of how a computer or a Java compiler compiles code. I need to learn that to help me understand how to optimize my code. And finally, how to implement physics into software. As you guys know, physics has a bunch of calculus in it, and even converting that into like a Word document is kind of a pain in the butt. It's even worse when you're trying to make it like actual code that you compile. Okay, so yeah, this is the University of Washington study I was talking about. Basically, after 2 months of research, I came across a study that said the effects of drag on the ball. I don't know why it took me 2 months to find that, but it really helped me out. First, it provided me these equations, which are for, the first one is drag, the second one is lift, and the third one is gravity, and those are the main forces that act on the ball as it's flying in the air. Additionally, if you guys know this equation, it looks kind of complicated, but it really isn't. The 0.5 is just a half when you convert forces into energy. The second is the coefficient of drag, which is just a number that shows what the influence of the force will actually be on the ball. And that's just something we determine through lab analysis. The second, the thing that looks like a P, is actually the Greek letter rho, and that is supposed to demonstrate the density of the medium that it's flying through. So in this case, the density of air. The A is the cross-sectional area of the object that's moving and the drag force acting upon. And p squared is the velocity of it, so that's what the equation is. The lift force is not different at all. The only thing that's different is it says the drag coefficient becomes the lift coefficient. And of course, the gravity, you all should know, is mass times gravity. So the University of Washington study, instead of having me do all the lab analysis to find the drag and lift coefficients, it gave them to me to the balance place, which is really helpful. And I didn't need to do any of that, so those are the drag and lift coefficients right there. And the density of air, quick Google search, 1.2 kilograms per meters cubed. The average mass of the tennis ball is 0.0585 kilograms. The average area is 0.0034 meters squared. So that's how he provided me everything I needed to fulfill the drag and the lift equations, except the velocity, which my partner gave me. Secondly, this was a large part of research dedicated to my project. It's using recursion, and what recursion basically is when you write a function to define what a computer program is supposed to do, basically call it within itself. That may sound kind of weird, but this demonstration shows it pretty effectively. So you have an input, let's say the square is the function, put the input in, and the function calls itself multiple times within itself, and then it goes into the output. So an example of this is this code. So this is basically a function to create a factorial of a number. For those who don't know, factorial is just a math operation. So 5 factorial would be 5 times 4 times 3 times 2 times 1. So if you plug that into this equation, the first thing you need to have in a recursion equation is a base case. So if statement for this one is if the integer is less than or equal to 1, you return 1. But for anything else, you return the factorial function that's called up here back into itself minus 1. So what this basically does is if you put in factorial of 5, it first checks if 5 is less than or equal to 1. It isn't, so it goes on to the else case, and it returns 5 times the factorial of x minus 1. So x in the initial case was 5, so it return x, which is 5, times the factorial of x minus 1, which is 4. And then 4 goes back into this, 4 is not less than or equal to 1, it returns 3. So now we're at 5 times 4 times 3, and 3 goes back into this. That 5 times 4 times 3 times 2, and then 1 goes in here. 1 is less than or equal to 1, so it returns 1, and it goes all the way back to be 5 times 4 times 3 times 1, which I think is 6. Now, here's a lot of my code. All of this is set up. This is a simple Boolean statement, so the main part of my project is this obscenely large mathematical equation right here. What this is basically doing is creates a unit vector for the velocity to get the direction, and then I'll use the previous equation that I showed you in the last slide to find the force of drag. I'll break it down using the opposite unit vector to get the components of the velocity that will affect, using cosine, sines, and angle between the x, y, and z components. And after I get those forces, I'll use the force equals mass times acceleration equation to find the actual change in acceleration, apply that to velocity, and finally you'll get the change in velocity at each increment. I think there's a for loop I can't quite see. The for loop is, I think it's at the increment of 50. This was a kind of a preliminary run. I can run this for loop at about 2.5 thousand right now with an adequate response time. So here are some simulations of the ball actually going. This is so the green dots right here are the initial coordinates that are passed by my partner, and then the red dots are 1/5 of the way through the ball trajectory, basically designs where the ball is, and the orange line is just a prediction of the trajectory, which is connecting the dots. So this helped me visualize if my application was working or not, and if you look at this, it's for basically roughing estimation, it works. I didn't really use it for flash with that. My accomplishments are I finally had a completed and theoretical model of the test ball in flight, and it actually works. We'll get to this into the screen modeling later. I actually had the calculation time of under 2 seconds for 2,500 calculations of that whole unit vector breaking down the drag force stuff, which is actually pretty good because it increases the accuracy to a margin of error of 1 inch. Possibly, this goes to say 10,000. Well, it's 10,000 increments while still staying under 2 seconds. That was a stretch goal. I don't know why this actually happens. I think it's because while the code is running, it needs to get an accurate image of the ball flying over the net before it can pass the actual statistic, the coordinates to my program. But sometimes the code can do up to 8,000 in under 2 seconds, and sometimes 8,000 takes 5 seconds. So I really don't know how to improve that for the research. Obstacles, there were quite a few major ones. The first one was wind. Originally, in our initial project presentation, it was a stretch goal. What we were planning on doing, if we have the time, is you guys probably know the Snapchat geofilters. Like if you swipe right, it will give you the temperature and time and altitude and whatever. What we wanted to do was get another third-party software that would use the location and would access the weather and get the wind speed. And that was only a stretch goal, and we did not have time for it because the actual implementation of the initial project took so long. But do you guys remember those like 2 or 3 days in like middle of March where it was basically a perpetual tornado outside? It was like 80 miles per hour consistently. We just had to go and test out the ball. And basically we just dropped the ball instead of falling right below it. The wind was so strong it would push it 3 to 4 inches to the side. So we didn't think wind would be that big of an obstacle, but it turned out to be. Unfortunately, we couldn't account for it in our product. Maybe we will. Additionally, spin. We'll show you a video representation of our project in the future, but there's pretty much no way to account for spin in this in a single Android camera. So the Magnus effect, which affects wind moving past a spinning object, will change the trajectory of the object. We were really hoping that that wouldn't cause much of a difference for a ball trajectory, and it turns out it doesn't. One study that I found by the University of Madison in Wisconsin, they spun up a ball to about 3,500 yards per minute in a machine, and they tossed it to see what the deviation from the landing spot would be. And it turned out it was only about 0.5 inches. Now, 3,500 rounds per minute is absolutely insane in the real world. No tennis player, not even a professional, will get that much. Like a professional player's slice will get about 400 rounds per minute at the high school level, which we're advertising to, maybe 100 to 150. So if it's only 0.5 inch difference with 3,500 rounds per minute, we're hoping that won't make too much of a difference when our application can be for high schoolers. But unfortunately, we have to get to that. Additionally, the efficiency of code, that took the majority of my project. Right now, we're sort of 2,500 increments in 2 seconds. At the beginning, I had about 103. So I really had to research what the compilation system of Java is and the processing system of a computer to realize how to actually figure out to optimize that code. This is a GIF video of our project working. So on the right, you will see the tennis ball in slow motion flying over the net. As you can see, it's pretty blurry, so I was talking about how we would be able to get a snip from that, but my partner did not know what was happening.
So it's basically what I was talking about. The ball isn't recognized by the OpenCV camera view, and that's what causes it to turn white, because the coordinate and range function output a layer of massive sorts. So whatever is not recognized by the program turns as black, and what was recognized, which is the tennis ball, but because it was in range of the matrix V values that are specified in the function, returned as white. So that's what we have going on here. And we didn't have a representation of the program actually drawing rectangles around the ball, or just one rectangle in this case. But that's essentially what that does.
And additionally, while this is running on the bottom half of our screen, this is what the computer is doing. It's doing the 2,500 increments of code. So it does the calculation of the drag force and change in acceleration every about 0.015 seconds to see where the ball will land. And at the end, it returns the final output, which is right here. It's kind of blurry, but I'm pretty sure you guys can see it. It returns the final coordinates and a bunch of previous ones. And the final coordinates, I think in this case, it's in centimeters. And right here, I think that says 234 centimeters. That says like 6 point something, but at the end it's -6, so that's basically 0, so that's when the ball hits the ground. And right here it's 360-ish. So what that means is the wall is 2.3 meters to the left and 3.5 meters long. And because 3.5 meters long is too long for a service, for a serve to begin, it also returns out right there. My expert advisors for me were Ms. Crapo. She's a physics teacher here at Danish. She teaches physics 1 to 3. And she's also an expert in grid cloud dynamics.
So my expert advisor was Robin Sullivan, and he's here today. He is an electrical and software engineer, also an independent consultant. Also, Terry Wood is another one of my expert advisors, and she is a physics teacher here at Grandview. She has experience in kinematics, which is obviously very important to this project.
My support advisors were first my mother. She was there for a professional software developer if I needed any advice. My father, who was mostly there for money. My friend, Andy Starr. He's there because he's good at physics and he can help me in this project. And my other friend, Sam Mock, who is also a friend, but in this case he's good at programming and complex.
So for me, my support advisors were first my dad. He is a professional software developer. Next is my mom, who was there for moral/financial support. And Andy Starr, we have the same peer support advisors. So Andy Starr and Sam Mock are my last two, and they both have physics expertise and programming expertise, respectively.
Okay, so this is my timeline. First color coding, green means I did it when I was supposed to do it. Yellow means I didn't do it when I was supposed to do it, but it got done somehow. And red means that I had to try. So November 2, the entire month of November really was basically the effect of drag on the ball and researching it. First was to integrate drag force. First right here was to create a basic model of where or some written form of how kinematics actually acts on the ball. And that got done, but I was way too naive and decided November 16th would be when I would integrate drag force. No, that didn't happen, so I had to research drag a lot more, which was good on my timeline. All of this red stuff because I was too eager to get stuff done. So I did end up starting a project in Java, and I set up version control in Git just so I'd have a history of my code. A lot of this is due to I started developing the program, and I worked on the program, trying to implement backwards without it crashing everywhere. Again, we were trying to incorporate WinForce, but we simply didn't have time to do that. Right here, this is when I basically got dragged to work, but it really wasn't accurate. The thing compiled, but it wasn't right. So I had to optimize the thing, and I had to get my code converted. Also, right here, improving the accuracy of the readings, that couldn't happen until this happened, so that had to be covered. Right here is finishing touches on the application. That also got delayed because of this. I think that was a month. This happened a month earlier. But right here, I started working with my partner to optimize the GUI, the graphical user interface of the application, to make it look pretty and make it so people would buy it. In March, we started making statistical trials of the ball. So we basically tried to hit the ball and see if the program would actually accurately predict where the ball would go. But what we found out was we did about 500 trials, and what we found out was the ball landed 1.2 inches away, at most 1.2 inches away from where the machine predicted it to be, which we thought was pretty good since coming into our project, our initial goal was to have a margin of error of 1 inch. So our 1.2 inch goal was almost met. Additionally, we also had tried to fix inaccuracies found by that. Initially, actually, it wasn't 1.2 inches, it was about 2.4 inches. We got that down to 1.2 by solving inaccuracies. Some of them were with the camera detection, and some of them were with my physics engine. So me and my partner got together in the last 2 weeks of March to fix those. And in April, basically finished the PowerPoint and finished our board. And get ready for the presentation. It's happening right now.
So this is my project timeline. So during October and November, it was mostly just research. So finding out how Internet Studio works, just the process of app development. And from November 1st to the 30th, I was tasked with starting to create the application GUI, the graphical user interface. And as time went on, so this kind of spilled over into December as well. So December was all about finalizing the user interface. So initially, as it says here, I had the options, the user options that I wanted to have on this interface were like open recorder, restart, quit back, things like that. But those weren't like needed, they weren't necessary. So in the end, all I ended up having was an open recorder. So that's the only option. Because at the end of the day, the user only gets one output, so in or out. So it's really, the rest of these options were really unnecessary. So although I completed them, I ended up scrapping them entirely. So from then on, I'd start requesting the camera permission to actually start recording and gathering the coordinates. And this last bullet point right here, from the 17th to the 31st, I wanted to not only have the user permissions for the camera requested, but also take a series of pictures and compile everything into one test run. But also this wasn't really necessary. I already had the user permissions requested for the camera, but compiling a series of test runs was really not necessary because at the end of the day, we weren't really set with the physics engine either. We were still working on our respective parts of the project, so having that part there at that point was not really important. So January was all about researching how to use the OpenCV library. So that's important because that software is what allows me to analyze the trajectory of the ball as it's going in real time in front of the Android camera. So from the 7th to the 21st, I was going to implement this research. So everything in yellow means that I was in the process of doing it, but I hadn't exactly completed it, but I was somewhere close. So you can see that here, improving the accuracy of the pictures taken. I was still taking the pictures and they were outputting the black and white layer mask, but I still needed to improve the function itself rather than just improving the accuracy. So that's what was happening there. And from January, the end of January and the start of February was just improving on accuracy and testing code, which I also did. So during February, this is the back end of February was when we decided to combine both of our projects together. So me with the coordinate graphing function and my partner with the physics engine. But again, we just weren't there yet. We were still working on our respective components. I was still working on the morphological image processing, so making sure I could get as clean an image as possible. And Danish was still working on modeling draft. So that wasn't going to work right there, so that's why that part is in red, because it was not completed then. So during the month of March, that was the statistical analysis time. So as my partner already stated, we ran 500 files to see where the program's accuracy was at, and we just kind of kept going from there and making changes as we needed to. And finally, during April, this was entirely dedicated to improving, creating our final presentation. This includes the board, the PowerPoint, and practicing and improving our publicity. So that's our bibliography, and while that's running, you guys have any questions?
How does the program's accuracy fare if the camera's not perfectly level?
Sorry, what was that?
Yeah, we didn't really test that out. I feel like that's something that the user would have to do because having the camera rotated and screwed up everything, it's not that hard to have it perfectly level mobile processing. It makes it so that there's a margin of error, so it's like 10 degrees over there, that was fine. Yet we didn't test it if it's like 45 to 90 degrees. Anything else?
How did you determine your bounds for your hue saturation values?
So that's what I was saying. For the on-touch color function, once I completed that, I literally focused in on a tennis ball, and I touched the screen where that tennis ball was. And that output the color value in hexadecimal, which then you can easily convert to hue saturation values. So basically, you need a range for that because not all tennis balls are going to be the same based on how much they're used or how new they are. They could have different shades of green. So they're not going to be the same color all of them, which is why you need to have a range that is acceptable for all tennis ball values.
So does a tennis ball being pressureless or pressured make a difference?
Guys, if a tennis ball is pressure or pressureless, does that make a difference?
What?
I don't know. Say it again.
So a balls are sold as pressured and pressureless. The pressureless ones bounce lower than the pressured ones. So does that make a difference?
There you go.
So we're not really counting for how high the wall is. We're literally seeing where it belongs the first time. So I don't think having a balance differential will have that doesn't matter.
Does your code take into account the different saturated value markers?
No.
And if you have like an object that's in the background, which is like of a similar color to the ball, and it picks that up as well, how do you exactly do that?
So essentially, like our program only takes into account like standard tennis balls, so like actual regulation tennis balls. But I'm pretty sure if you wanted to change what color that you were really picking up, all you have to do is change the key saturation values. So that shouldn't be too hard to change. And also in terms of picking up different objects that are in the background that are the same color as the tennis ball. So that's where the fine contours part of this comes in. So essentially, if a larger background is returned, I have an if statement in the code that says that contours can only be drawn in the event that they're of a certain size. So which means that the contours that are drawn are only explicitly for the tennis ball size itself. So it's unlikely to pick up anything else, but it could still be a possibility if there was something in the background, like two tennis balls that were the exact same size and color.
What you guys learn about refactoring? That's software engineering refactor is the promise that you go back to your product and take care of things. Oh, you know, this is a mess here. I can just split this off. This goes into this function.
Totally agree with that.
What you guys do with the thing about me?
So for me, most of it was optimization through my version control. I could show you the link, maybe nice and happy, but through my version control, you can go through the history of my code. You'll see it gets shorter and shorter and shorter. At the first point, I had so much unnecessary stuff in my for loop that really didn't matter. And I need to take that out, and that's where I learned about the compilation stuff. And because of the version control, I could really refactor and refit my code into something that would be more efficient.
So in my case, I guess it's really getting down to improving the accuracy of the images that were taken. So previously, I only had the output based off of hue saturation values and nothing else. But later on, I learned about these different operations that you could use to get rid of the background noise and improve the accuracy of, or just get rid of the holes that are inside of the image itself. So I guess I refactored my code to make sure that, that the image that was detected was more accurate.
So the prompt was really learning that refactoring is part of software engineering.
Yes.
Yeah.
That's good. Okay, thank you.